This video is designed to help you understand what we mean by graph transformations and what's going on if you look at a parent graph, which is the kind of basic version of a specific type of graph, and what happens when you put variations in there with some of the constants or variables floating around it. So let's start with the basic idea of what happens when you transform a linear equation, which we should be fairly comfortable with. So the parent graph, as I've shown in the first graph, is y equals x. I'll put arrows on it to indicate that it continues on. And the parent graph goes through the origin, so I'm going to identify that it goes through 0, 0. And it tilts at 45 degrees, so it has a slope of 1, as we know here. So I'm going to put the 1 in there just to kind of remind you. And what that means is its tilt is change in y over change in x, so a change in y would be 1 over every change in x would be 1, or 2 over 2, or 3 over 3, and so on. So a variation on that, which would be a graph transformation, would be y equals x plus 3, which is the second graph in the upper right. I've graphed that for you. Let me put the arrows on that as well. Pretty bad arrow. And the idea is what happens when you add 3 to the parent graph of y equals x. So in other words, it's y equals mx plus b, which is kind of what we're used to. We're used to this idea of the general form being y equals mx plus b. What we're saying with graph transformation is when we add 3 to y equals x, then every y value is 3 higher than for the corresponding x. So if you plugged in x equals 1 on the first graph, you'd get y equals 1. If you plug in x equals 1 on the second graph, you get y equals 1 plus 3 or 4. So that means if you were making your input-output tables, you'd get x equals 1 and y equals 4 over here, whereas of course for the parent graph, when you put in x, you get out the same value for y. So we know that that's a graph transformation, and that says, what happens when you change b? Well, the whole graph shifts up. And now what we know is that it goes through 0, 3 at this point, the y-intercept, which is something that we talked about a lot. So just to kind of remind us as well, if you did something like the graph, say y equals 1/2 x minus 2, what that would tell you is that you would take the parent graph and it would be flatter, and we know that it would shift down because b is -2. So it would shift down 2 points. So we'd know that we'd come up with a graph that would look something like this. I'll just sketch it quickly. So it's going to be flatter because the change in y over change in x is now 1 to 2, 1/2, and we know we're at this vertex, this y-intercept of 0, -2. So those are some transformations that are occurring to the parent graph of y equals x, the most basic graph that you can have with a linear equation. And of course other variations, as we've seen over the years for these, transform it into a different graph. So let's take a look at some other parent graphs on subsequent slides. So on this second slide, I'm using function notation now to kind of remind us that we're dealing with functions. So I've said f of x equals the absolute value of x. Now when x is, and let's make our input-output table of x and f of x. When x is positive, let's say x is 2, we're going to get f of x equals 2. When x is 1, we're going to get f of x equals 1. When x is 0, we're going to get f of x equals 0. So far, it looks like our linear equation, but then it bounces, and it hits the bottom of a valley, if you will, and it bounces back the other way, because if you put in x equals -1, you get 1 for f of x. And if you put in x equals -2, you get 2 for f of x because you're taking the absolute value. So what that means is the parent graph has a vertex, okay, at 0, 0, because the lowest point that it's going to hit is when x equals 0. So how can we change f of x equals the absolute value of x? What are the variations we can put into it? Well, we can add c again, which would shift it up or down based on whatever the value of c is. So I'm going to mention that if you change c, it shifts it up or down. What happens if we change b? Well, b is actually going to shift it left or right. What that means is that vertex, that bottom point, is going to be where x plus b is 0, because that's the lowest it can go. Unless, of course, a is positive or negative, or rather negative, in which case the whole thing is flipped upside down and it's a mountain and we're talking about the peak. We'll get back to that in a couple of slides. But the thing to recognize is, let's say I took the equation, the function f of x equals the absolute value of x minus 2 plus 1, let's say. What that says is, if x is 2, and let's take a look quickly at the input-output of f of x and f of x. If we put in, let's say 4 for x, then 4 minus 2 is 2. Absolute value of 2 is 2, plus 1 is 3. So let's put in 3 for x. Then we're going to get 3 minus 2 inside the absolute value brackets. 3 minus 2 is 1. Absolute value of 1 is 1, plus 1 is 2. If we put in 2 for x, we're going to get 0 in our absolute value. In other words, x and -2 cancel each other out, and so the absolute value of 0 is 0, and we're going to add 1 to that, and we're going to get 1. Now, what we also get, though, is we'll notice that if we put in x equals 1, then the absolute value is no longer 0. So 1 minus 2 is -1. The absolute value of -1 is positive 1. 1 plus 1 is 2. And if we put in 0 for x, we're going to get 0 minus 2 inside the brackets, which is -2. The absolute value of -2 is positive 2, plus 1 is 3. And so what you'll notice is that the low point is when x and the b value, in this case -2, cancel each other out. They have to compensate for each other. And of course, when the absolute value is anything other than 0, it's a positive number, and it's going to add to the value of f of x. So the bottom is going to be when x is 2. So what we're finding is that we can locate this vertex by simply saying, here's the x value of the vertex, and here is the y value of the vertex. In other words, the bottom of this graph is going to be at 2, 1, which we'll mark over here right now. So 1, 2, okay, we'll go up 1. So there's 2, 1, and the rest of the graph then is going to look like the normal absolute value graph. It's just going to be shifted over 2 to the right, and it's going to be shifted up 1 because of adding 1 for c. So play with that a little bit yourself, and you'll see that b shifts it left or right. If b is negative, then x has to be bigger, positive, to compensate for it, to find that 0 point. So what we're going to try to do is locate that vertex every time with a graph that has a vertex, just like we tried to locate the y-intercept on linear equations. So let's move on to the next slide and see, take a look at a few others. So I've written a couple more absolute value equations, and you can see that the only things I've changed are b and c. I haven't messed with a yet, it's still 1. And you might want to pause this video and try for yourself to see what they are. Make yourself some input-output tables of x, f of x, and see what you get, and try to plot some points. And remember that what you're looking for really is try to identify the vertex and then build some points on either side of the vertex to make sure that you're working from an absolute value V structure, like a valley structure. Okay? Pause the video and try that, and then I'll be back. So let's take a look at what these graphs look like, and I'm going to tell you that this first graph on the left is going to give you a vertex at x equals -3 and y equals -2. So we're going to just make a vertex right here, x equals -3 and y equals -2. Let me label that. -3 comma -2 is the vertex. And if you make your input-output table, you'll see that that's the lowest value that f of x can be. And from there, it's simply going to go up in its classic V form. So this would give your graph for f of x equals the absolute value of x plus 3 plus -2. So in other words, when x equals -3, the absolute, what's in the absolute value sign, brackets, becomes 0, and f of x is just -2. It's just that c term. Let's take a look at the other graph, and we'll see a similar kind of thing. We should be able to identify that the vertex immediately is x equals 1 and y equals 2. So we're going to make that vertex of 1 comma 2. That is, when x is 1, 1 minus 1 is 0, and we get 0 in the absolute value sign. So you're absolutely looking, no pun intended, for the value of x that makes what's in the absolute value sign 0. As soon as you have that, then you've identified the lowest value of f of x as long as a is positive. And of course, our graph from here extends off like this. So on the next slide, we'll take a look at some other variations. So on this first graph, f of x equals 2 times the absolute value of x minus 1 plus 3, we still have the same vertex. That is, when x is 1, the value inside the absolute value sign is 0. The absolute value of 0 is 0, of course. 2 times 0 is still 0. So we still bottom out at x equals 1 and y equals 3. So let's draw that vertex of x equals 1 and y equals 3. So there we go. There's 1 comma 3. 1 comma 3 is our vertex. And what happens now? Well, instead of going up at a steady rate of 45 degrees, one change in x adds a change of 1 in x adds a change of 1 in y. We now have a steeper slope because a is 2, which means that every time x, or what's in the absolute value, changes by 1, the value of f of x increases by 2. So this is like having a steeper line in your linear equations as well. Obviously, if it was 1/2, it would be flatter. So A makes it steeper or flatter. So I'm going to say it like this. If A is greater than 1, then it's going to be steeper. And if A is between 0 and 1, it's going to be flatter. So you're getting you've flattened out the lines that you're normally looking at. And we'll look in the next graph what happens if A is negative, because of course we've just considered the positive cases. So what that means is our graph is going to be a little bit steeper than it was before. It's going to go up with a slope of 2, so it's going to be a steeper V, or a sharper valley if you want to look at it that way. And that's what our graph would look like. Let's take a look at this final one on this slide. And of course, our vertex is once again going to be at x equals 1 and y equals 3. So it's exactly in the same place as the previous one. There's our vertex again. Vertex of 1 comma 3. Let me make that 1 comma 3. And now what we have is, again, a steep slope of 2, but it's actually negative 2. And what that means is every value of x that contributes to having the absolute value being something other than 0 is going to subtract 2 for each one value of x that occurs. And so what that means is, instead of having a valley, we have a mountain with a slope of 2, and our graph is going to look like this. So you can plot some points for yourself and see that, but what we've done is, if a is less than -1, then it's going to be steeper, but it's a steeper mountain. And if a is trapped between 0 and -1, it's going to be flatter. And once again, this is the same system as you would get when you were graphing linear equations. And of course, if you look at the absolute value graphs, it is 2 linear equations that just bounce off this vertex. So you're graphing linear equations. It's pretty straightforward as far as that's concerned. So focus on the vertex. That's identified by whatever compensates for b. So if b is -1, as in this case, then x has to be +1 to make the inside of the absolute value sign 0. And then whatever c is your y value, or your y coordinate value for the vertex. Focus on the vertex and sketch the graph the way you know it looks. Let's look at one more slide. So these two graphs are what we call quadratics. Both of them have an exponent of 2, although that first one doesn't really look like a 2. Remember, it's a 2. These are exponents. So instead of absolute value, we have x minus 1 squared. So what that does is it changes. We do not have a steady slope, because as x increases and we square it, what we do is get steeper and steeper. So the parent graph for y equals x squared, so y equals x squared, or f of x equals x squared, the parent graph is what's called a parabola, and it's going to bounce at 0, 0. Sorry, it isn't drawn very well, but it's going to bounce at 0, 0. And that is, as x increases, y increases by the square of x. So it's going to get steeper and steeper, and you're going to get a graph that looks like this and continues to get steeper and steeper. It's often drawn as sort of a U shape, and it's called a parabola or a quadratic. So parabola is the shape. Parabolic mirrors you may have heard of. And it's also known as a quadratic, which has to do with the fact that it's a squared exponent. So that we'll talk more about this later. But at any rate, a parabola is going to look like that. So those are the parent graphs. And you may think about this exactly like the absolute value graphs. You're going to get, instead of a V shape, you get a U shape, but everything else is exactly the same. Because it gets steeper faster, that's why it curves up as opposed to just being straight lines, because of the exponent. And you can try some points for yourself with y equals x squared, and you'll see that it gets steep very, very fast. But the vertex focus can be exactly the same, and what A is doing can be exactly the same. So in the same position, we'll think of B as the value inside the parentheses with x, trapped in there with x. We'll think of C as this guy, so that's C, this is B, and this is A. So you might want to pause the video and think, what's this one going to look like? And then we'll take a look. Okay, if you're back, let's take a look at what this looks like. We should have a vertex once again, so x has to compensate for subtracting 1. So when x is 1, you're going to be the lowest possible value that you can. So when x is 1 and c is -3, we're going to get our vertex of 1, -3. Now on either side of that, what you're going to get is, let's say when x is 2, you're going to get 2 minus 1, which is 1. 1 squared is 1, times 2 is 2. 2 minus 3 is -1. So you're curving up. So you're going to get a point over here, 2, -1. And what you're going to find is the graph is going to look like this. And it's going to look like this. And it's going to curve up. And you can, of course, find the y-intercept by putting in x equals 0. When x is 0, you get x minus 1 is -1. You square it, it becomes +1 times 2, which is also 2. And then subtract 3, so it's -1. So I haven't made this beautiful. It should probably go up a little steeper like that. But at any rate, you're going to get this kind of parabola. And any value you want, you can find. But focus once again on the vertex, which can be identified in exactly the same way. And finally, let's take a look at this last one. Now, by the way, on this first one, of course, with the coefficient a of 2, that means that it's going to go up even steeper than it normally would, because every change in x that gets squared, then you double that change. You know, that's like doubling, you know, y equals 2x plus 3 or something for a linear equation. It becomes a steeper line. So this becomes a steeper parabola. You'll notice on the last graph here that we have a equals -1/2. So we should be able to identify the vertex again. X must be -2 to compensate for adding 2, and that'll give us 0 in our squared. So -2 and -1. So our vertex is -2, -1. Okay, but now since it's a negative a, it's upside down, and since a is 1/2, it's also flatter. It doesn't move up quite as fast. So what we're going to get is a parabola that looks a little more like this. Not very well drawn, sorry about that. It's going to look something like that, with the high point being the vertex of -2, -1. I hope this has helped give you a rough idea of how to sketch some graphs. You can, of course, find y-intercepts. Sometimes you can find where it goes through the x-axis. You know, on this one, if you wanted to find the y-intercept, simply plug in x equals 0. You're going to get x plus 0 plus 2 is 2. 2 squared is 4. Half of 4 is 2. The opposite of that is -2. So what you're going to get is -3. So of course we now know that this point right here is going to be 0, -3, if I did that calculation correctly. 0 plus 2 is 2. 4, half of 4 is 2. The opposite of that, so it's -2 minus 1 is -3. Yes. Okay, so I hope this has helped.